Hey, welcome back to Real Analysis, Math 316. In this video lecture for section 1.8, we're going to talk about a proof technique called induction. Probably became familiar with the technique of induction in your Math 240 course. It's a technique that we'll use certainly, somewhat often here in this course. But why stop and have an entire discussion about it? Well, I kind of want to give you an illustration that this proof technique of induction is really a mathematical theorem. It's stated here on the front screen here. It's theorem 1.13 in our book. And so I want to give a proof of the theorem. The proof of it is actually going to come from another fact that we'll talk about called the well-ordering principle, that by itself relies on this completeness axiom in the real numbers. So really, we're just sort of taking a chance to illustrate again this kind of deep property of the real numbers, that every set that's bounded above has a least upper bound, and every set that's bounded below has a greatest lower bound, this completeness axiom. So these kind of deep facts about the real number systems are at the bedrock of everything that we're doing in our course. Okay, so the author has their statement of the mathematical induction theorem here. It says that if you take a subset of the natural numbers called S, and it kind of has two properties, that one belongs to S, and then whenever you have a number n in S, the number n plus 1, its successor is also in S, then S actually has to be the entire set of natural numbers. I'm just kind of rewriting that at the bottom of the screen in sort of more of a kind of a checklist form. So in particular, if you have this subset of the natural numbers and it kind of satisfies two properties, that the number 1 is in it. It's usually called the base step when you're using this as a proof technique. And then the inductive step is the second property, that whenever a number belongs to S, its successor, the natural number that's 1 bigger than it, also belongs to S. Then S actually doesn't have any holes in it. It consists of the entire set of natural numbers. Okay, so that's the theorem. I wanted to start by kind of illustrating it. I'm picking something, you've probably proved this by induction several times, but it's kind of a quick way to illustrate how the theorem works, and in particular to illustrate how it works in the notation of the theorem in our section. So the statement that I'm going to show is that if you add the first n counting numbers, so you take the sum of the first n natural numbers, that sum is always equal to the product of n times n plus 1 over 2. Right? So that's the statement I'm going to show. For every n, that formula holds, and I'm going to prove it by induction. So when you're showing some formula holds for all n by induction, and you want to use the framework of the way the theorem was stated, you basically let your set S denote the set of natural numbers for which the statement you're trying to prove is true. So I'm just going to declare the set S to be the set of natural numbers for which that formula holds. The sum of the first n natural numbers is the product of n times n plus 1 over 2. Okay, and then my job is to show you that S satisfies those two conditions, that 1 belongs to it, the base step, and it has the inductive property that whenever something belongs to it, so does the successor. And if I can do that, then the principle of math induction says that the set S is all natural numbers, which is just a way of saying that this formula holds for every natural number. All right, so to check the base step, well, I mean, I've got a formula. I can just plug in n equals 1 on both sides. On the left-hand side, n is the number of summons. So if I let n equal 1, that left-hand side of the formula, it really just has one term, and it's a 1. And the right-hand side of the formula would be, well, 1 times 1 plus 1 over 2, and those quantities are clearly equal. They're both equal to 1. So that's the demonstration that the base step holds, that the number 1 actually belongs to the set S. So now for the inductive part, I have to assume its hypothesis. I'm going to suppose I've got some natural number that belongs to the set S. So what does that mean? That means that this formula holds for my natural number. What is my natural number? I don't know. It's some number greater than or equal to 1. And I'm supposing that this formula holds for it. And then I need to show this formula holds for the next number. I need to show n plus 1 is in S. Right? So how am I going to do that? Well, I'm going to start by considering the sum of not the first n numbers, but the first n plus 1 numbers. So if I scroll down here, I think I'll just show it all. So that's what I'm starting with. I'm starting at looking at the sum of the first n plus 1 natural numbers. All right, so that's what the sum would look like. And then to use the fact that n itself is in S, if I focus on the first n terms in that sum on the left-hand side, well, the fact that n belongs to S means that those first terms, add up to this expression, n times n plus 1 over 2, right? That's exactly where I'm using the so-called inductive hypothesis, that the number n does belong to S. So what's with this remaining term? Well, I mean, it was still there. I can't just ditch it. So I'm just replacing the blue bracketed term with what it equals in closed form by my induction hypothesis. And now I'm just going to do a little bit of algebra. I left it out of the video here, but I can certainly multiply this second term by 2 over 2 to get a common denominator, and then just factor out the n plus 1. And so that's how I arrive at this expression down here. I'd have n plus 1 times the quantity, n plus 2, right? That n plus that 2 is my second factor. That's all over 2 because that's the denominator of the fraction. And n plus 2 is certainly n plus 1 plus 1. Yeah. So what have I shown? The sum of the first n plus 1 numbers is the product of n plus 1, the number that's 1 bigger than that, over 2. That exactly, by definition, shows that n plus 1 is in S. So we've met conditions 1 and 2, and so S is equal to all natural numbers by the principle of mathematical induction. Cool. Okay. So I want to prove the principle of mathematical induction, and how am I going to prove it? Well, it's actually equivalent to, but I'm not going to worry about that in this video lecture, to this statement that the book calls the well-ordering principle, Theorem 1.12. The well-ordering property, well-ordering principle, same thing, same acronym. So what does it say? It says that every non-empty subset of the natural numbers has a smallest element. Okay, smallest element, or if you prefer, in the language of our previous sections, it has a minimum. So there's some element, every non-empty subset of the natural numbers has some element that's in that subset, and it's less than or equal to every other element of that subset. So smallest element and minimum in the sense of previous sections are synonyms. All right. Why is this coming up in an analysis class? Well, this well-ordering principle requires us to have the completeness axiom of the real numbers. Okay, so let's see if we can't check that out. So to start our proof, let's take some non-empty subset of the natural numbers. I'm going to call it S. So I've got some set S. It's not empty. It has something in it, and it's a subset of the natural numbers. Okay, the natural numbers themselves are bounded below. They're bounded below by 1 or 0 or whatever you like. They're bounded below in the set of real numbers. And S being a subset of them, well, S is bounded below as well. Right, so that's how I'm going to start, is that S, this set, is bounded below. So by the completeness axiom, it has a greatest lower bound. I'm going to call that greatest lower bound V. Greatest lower bound, or infimum, and the notation we use is this INF, inf of S. So what is V? V is a number that is, well, first of all, less than or equal to every number in S. And second of all, any other number that's less than or equal to every number in S is greater than or equal to V. Right? So it's the least upper bound of the set S. And then let's just do away with a case. If V happens to belong to S, then it's the minimal element and we're done. Right? So if V, this infimum, belongs to the set S, then it's certainly the smallest element of the set S, and we're done. All right, so sorry about kind of the poor notes here, but I'm going to go ahead and say, so let's assume, we may assume is my on-the-fly acronym, that this set V does not belong. So this element V, excuse me, does not belong to the set S for the rest of the proof, because if it does, we're done. Okay, so continuing along here, I'm going to use some ideas about the greatest lower bound. The number V plus 1 is certainly bigger than V, right? So if you're bigger than the infimum, you cannot be a lower bound, right? The infimum is the greatest of all the lower bounds. So anything that's bigger than the infimum cannot be a lower bound. So if you're not a lower bound for the set, there must be something in the set that's less than you, right? Because you are not greater than or equal to, or so sorry, you are not less than or equal to everything in this set. You're not a lower bound. This element X is in the set S. We've already said V isn't. It's what we're assuming in this case. So this X is between V and V plus 1. All right, good. Let's note again that because X is bigger than V, X itself cannot be a lower bound for S. V is the biggest of all the lower bounds of S. Anything bigger than V cannot be a lower bound for S. So it's X is bigger than V, same reason as V plus 1. X cannot be a lower bound for this set S. V is the infimum. Okay, so what does that mean? Well, that must mean there's some element Y, and Y belongs to S, but it's less than X. Yeah, because X can't be a lower bound for the set S. There has to be something in S that's smaller than it. This element Y is in S, so it's certainly at least as big as V. In fact, it's strictly bigger than V, I guess I could say, because we're in this case assuming that V is not an element of S. But still, I'll just leave the inequality like that. Okay. So what have we got then? We've got this element Y. It's strictly less than our element X. And that strict inequality is between V and V plus 1. If you string them all together, maybe you need to stop the video and go back and kind of move these inequalities around and make sure that you agree with this string of inequalities. So I've got these two numbers, Y and X, and they're strictly, Y is strictly less than X, and they are between V and V plus 1. And like I said above, I'm going to erase some of this. Well, I guess I'm writing it down here. I don't need to erase it. If V is equal to Y, that would force V to be in S again, and it would be smallest. But we were saying that V isn't in S, so this really can't happen. Yeah. So what am I stumbling about? I'm saying that this inequality is really strict as well. If it isn't, then I've kind of contradicted the case that I'm in. So maybe if I had a chance to remake this video, I would have done that right here. But V cannot equal Y, because if it is, it's trivially the smallest element. Cool. All right, well, if V is strictly less than Y, then the string of inequalities that we're looking at are strict. Right, so I've got Y and X strictly between V and V plus 1, but the difference between V and V plus 1 is 1. So that means the difference between X and Y, subtracting the smaller value from the bigger one, would be between 0. Why is it greater than 0? Well, because X is not equal to Y, so this difference is positive. Why is this difference less than 1? Well, because it's less than the difference between V plus 1 and V, which is equal to 1. All right. But X and Y are natural numbers because they're elements of S. S is a subset of the natural numbers. Everything in S is a natural number. So the difference between X and Y is an integer. The only reason I'm not writing it's a natural number, I guess yeah, I could write it. It doesn't matter. It's a whole number. But there are no whole numbers strictly between 0 and 1. So that's a contradiction. So what is the contradiction? What did we contradict? We contradicted our assumption. Let's just go back. We contradicted our assumption that V or that we contradicted the assumption that S has no smallest element. Sorry, I lost my train of thought there. So that's the proof of the well-ordering principle. Every non-empty subset of the natural numbers has a minimal element. There's an element in that subset that's smallest. So from that, I'm going to give a proof of the principle of mathematical induction. Again, maybe in your logic course, you might have seen that the principle of mathematical induction is actually equivalent to the well-ordering principle, but I'm going to satisfy myself with just a one-directional proof here. So I want to prove theorem 1.13. I stated it here again, that if S has this property, it's a subset of the natural numbers, and it contains the number 1. And whenever an element is in it, the next element is in it, then it has to be everything. So I'm going to proceed by contradiction here again. I'm going to suppose that I've got some subset of the natural numbers. It's got 1 in it, and it has this inductive hypothesis. And whenever n is in it, n plus 1 is in it. But for a contradiction, I'm going to suppose that S isn't the set of all numbers, natural numbers. And I'm doing that in a slightly more specific way. I'm going to let T denote the complement of the set S. So those natural numbers that are in N but not in S. And if S is not equal to the entire set, then its complement is not empty. Okay, so I'm kind of supposing for a contradiction that the complement of this set S isn't empty. Well, by the well-ordering principle, a non-empty subset of natural numbers has a smallest element. Let's call it V. Okay, so there's some element V in T, and it's less than or equal to everything else in T. So it's the smallest element. It's by the well-ordering principle. That number V can't be 1, right? Because T is the complement of S, but we're saying that S contains 1. 1 cannot simultaneously be an S and its complement. So whatever this V is, it's at least 2. Okay, so why do I care about that? Well, I care about that so I can say that if you're a natural number that's at least 2, then U minus 1 is also a natural number. So V minus 1 is also a natural number, and V minus 1 is certainly strictly less than V. And because V is the smallest element of T, it's still visible here, yeah, then V minus 1 cannot belong to T. It's smaller than V. V is the smallest element. But if you're not in T, remember, T is just the complement of S. So if you're not in the complement of S, then you're in S. There's a lot of kind of logic going on here, but this element V minus 1 must belong to S. But we're assuming that whenever something is in S, the number that's 1 bigger than it is in S. So if I take my V minus 1 and I increase it by 1, I certainly get V, and the inductive hypothesis says that that has to be an S. But now we're in kind of a contradiction space here, because I'm saying that the number V is in T, it's the complement of S, but the number V is also in S. Well, no number is in S and its complement, right? So that's our contradiction. So that proves the theorem. All right, so I hope that that was fun to listen to. Thanks for listening.